Welcome to the deep dive. Today we're tackling a really core concept for anyone building or, operating distributed systems.
Yeah,
And
absolutely.
it comes up a lot in senior tech interviews too. Quorum consistency, specifically in leaderless replication.
Right.
So our goal today is really to dig into how these quorums work, how they try to keep data consistent, and maybe explore some of the tricky parts, the potential pitfalls.
Exactly. It's all about getting agreement, fundamentally,
Yeah.
across a bunch of machines when things might be failing. And the quorum ID itself is, well, it's central. You need a certain number of nodes to, sign off on reads and writes.
Okay, let's break down the basics then. We always hear about N, W, and R. Can you quickly define those for us in this context?
Sure. So N's pretty straightforward. That's just your total number of replicas for a piece of data.
Total copies. Got it.
Yeah. Then W is the write quorum. It's the minimum number of nodes that have to confirm a write worked before you tell the client, okay, it's written.
Okay, W for write success,
Yeah.
and R.
R is the read quorum, the number of replicas you need to contact and get a response from when you're doing a read.
Right, okay. And that leads us to the magic formula, right? W plus
Equal-
R greater than N. What's the thinking behind that specific condition?
Yeah, W plus R greater than N. The key insight there is overlap. It mathematically forces the group of nodes you successfully wrote to.
The W nodes.
Exactly, the W nodes,
Right.
and the group of nodes you read from.
There it is.
To have at least one node in common, there has to be an intersection.
Ah, I see. So because there's an overlap, you're guaranteed or almost guaranteed to hit a node that saw the latest write.
That's the idea. It makes it highly probable, yeah. That overlapping node should, in theory, have the most recent value you're looking for.
Okay, that makes a lot of sense. So people often talk about majority quorums. How do they fit into this W plus R greater than N picture?
Majority quorums are a really common way to make sure W plus R greater than N holds true. Typically, you set both W and R to be just over half of N, so greater than N divided by 2.
Right.
If you add two numbers that are each bigger than half of N, their sum has to be bigger than N.
Yeah, mathematically, that works out.
And the big advantage is fault tolerance. A majority quorum setup can usually handle up to N divided by 2 nodes failing, and you still maintain that potential for overlap between reads and writes.
Okay, so quick example. If N is 5 replicas, a majority is 3.
Exactly.
So you'd need W to be at least 3 and R to be at least 3.
Yep, 3 plus 3 is 6, which is definitely greater than 5.
Right. So you could lose 2 nodes there and still hopefully get reads and writes to overlap.
That's the resilience it buys you.
But hang on, you said highly probable and potential for overlap earlier. So it's not an absolute 100% guarantee, even with W plus R greater than N.
That is a really critical point. No, it's not an absolute guarantee in the messy real world. Distributed systems have, well, complexities, but also majorities aren't the only way to do it. You could choose other values for W and R. Maybe you want really fast reads, so you make her small. Then you'd have to make W quite large to still satisfy W plus R greater than N.
Ah, okay. So you can tune W and R for different performance characteristics as long as they add up correctly.
Exactly. It gives you flexibility in how you design your system, maybe optimizing for read speed or write durability, depending on what your application needs most.
Interesting. So, okay, let's flip it then. What if you don't meet that condition? What if W plus R is less than or equal to N?
Well, then you're significantly increasing your chances of reading stale data
How so?
because there's no guaranteed overlap anymore. It becomes entirely possible for your read operation hitting R's to completely miss all the W nodes that receive the latest write. If that happens, you're definitely getting an old value back.
Okay, that sounds bad for consistency, but I assume there's a reason people might configure systems like that. What's the upside?
The trade-off is usually about latency and availability, performance, essentially. If you only need, say, 1 or 2 nodes to respond for a read or write, or W or small, that operation can finish much faster. That's huge for some applications.
Makes sense. Less waiting.
And availability, too. The system can keep accepting writes as long as at least W nodes are up, and serve reads if at least R nodes are up. So even if quite a few nodes are down, you might still be operational.
So you're trading consistency or the probability of consistency for potentially better speed and uptime.
Exactly. Think about use cases where maybe it's okay if data is slightly out of date for a short period, but the system absolutely needs to be responsive and stay online. Eventual consistency is often the model here.
Okay, so that covers the basic quorum idea and the trade-offs, but you hinted earlier, even when W plus R is greater than N, things can still go wrong. We can still get stale reads.
Yes,
Yes.
this is where the real-world complexities bite. Even with the math seemingly on your side, there are edge cases.
Okay, this sounds like the really interesting part. What kind of scenarios can break that quorum promise?
Well, one common one is something called sloppy quorums.
Sloppy quorums.
Yeah. So normally you think of writing to a specific set of W nodes and reading from a specific set of R nodes. And the overlap is between those sets.
Right.
With sloppy quorums, especially under high load or partial network failures, a write might get accepted by any W available nodes, maybe not the primary ones for that data, then a later read goes to the correct R nodes.
But those might not include the sloppy nodes that actually took the write.
Precisely. The write succeeded, technically met its W count, but the read operation might completely miss the nodes holding that latest data because the write landed somewhere unexpected. The overlap assumption is broken.
Ah, okay, that makes sense. The definition of who is in the quorum gets a bit loose. What else? You mentioned concurrent writes earlier, too.
Right. Concurrency is always a headache in distributed systems. Imagine two clients try to write to the same key at almost the exact same moment. Different replicas might see those writes arrive in different orders because of network latency. So which one is actually the latest? It's ambiguous.
So how do systems handle that?
Well, one good way is to have mechanisms to merge the conflicting writes if the data type allows for it. But a very common approach is last write wins, or LWW.
Based on timestamps.
Usually, yes. Each write gets a timestamp, and the write with the later timestamp is considered the winner and overwrites the other.
Seems reasonable, but what's the catch?
Clock skew. If the clocks on the different server nodes aren't perfectly synchronized, and they rarely are, a write that actually happened earlier might get a slightly later timestamp by mistake.
Oh,
Yeah, so the genuinely newer data could get overwritten by older data just because of slightly off clocks, data loss, essentially.
Yikes. Okay, the perils of time. What about reads and writes happening at the same time? Concurrent read-write.
Another tricky one. Let's say a write operation starts. It sends the new value out to the replicas, but maybe it's only reached, say, half of the W nodes it needs when a read operation kicks off. The read contacts its R nodes.
And because W plus Rn, that R set should overlap with the full W set.
It should overlap with the intended final W set, yes.
Wow.
But the write isn't finished yet. So the read might hit some nodes that have the new value and some that still have the old value.
So what does the read return?
It's often indeterminate. Depending on exactly which R nodes respond first and how far the write has progressed, the read might return the old value or might return the new value. It depends on timing.
So even with the numbers right, the exact interleaving of operations can mess things up. Okay, what other gremlins are there?
Partial write failures. This one's subtle. A write goes out to, say, all-in replicas.
Okay.
Maybe it succeeds on enough nodes to meet the W threshold. The system tells the client, yep, write successful.
Great.
But maybe it failed on some other replicas. Perhaps a disk was full or there was a temporary network glitch just to that one node. The overall write was still counted as a success based on W.
But not all nodes actually got it.
Exactly. And typically, those successful writes aren't rolled back. So now you have a divergence. Some nodes have the new value, some have the old. A later read, well, it depends which nodes it happens to hit within its R quorum. It might see the new value, it might not.
Wow. So a successful write doesn't actually mean all the intended nodes got it uniformly. That's important to realize.
Very. And then there's node failure and recovery.
Right. Nodes go down, they come back up.
Imagine a node that has the latest version of some data fails. It's down for a while. When it comes back up, it needs to get its data back. Maybe it recovers by copying data from another replica.
Okay.
But what if the replica it copies from happens to have an older version of that data?
Uh-oh. So the recovered node now has stale data.
Yes. And now the total number of nodes holding the absolute latest value might have just dropped below W. So for a period, even reads that satisfy the GAR quorum might fail to find a node with the latest data because one of the nodes that should have had it got overwritten with old data during recovery.
Man, it really feels like there are lots of ways for this quorum guarantee to get temporarily broken in practice.
That's a good way to put it. It's not necessarily that the W plus R greater than N logic is flawed. It's that the dynamic nature of distributed systems failures, concurrency,
Hmm.
timing, introduces scenarios where the assumptions behind the simple overlap guarantee don't quite hold.
Yeah.
And there are even more subtle timing things too, deep implementation details. The big takeaway is that quorums, especially with W plus R greater than N, give you a strong probabilistic chance of getting the latest data in leaderless systems.
But not certainty.
Not absolute certainty, not without other mechanisms layered on top.
Which really explains why systems like DynamoDB, Cassandra, these leaderless systems are often talked about in terms of eventual consistency, right?
Right.
The W and R are knobs you tune to make stale reads less likely, but not impossible.
Precisely. They're often built for use cases where that trade-off, high availability, partition tolerance, even if it means some potential for briefing consistency, is acceptable. You have to realize that the stronger guarantees you might get elsewhere.
Like read your rights.
Yeah, or monotonic reads, consistent prefix reads, those generally don't come for free with just basic quorums in a leaderless setup. You usually need more complex things like distributed transactions or consensus protocols like Paxos or Raft to achieve those.
Okay. So if you're operating one of these systems, how do you even know how much staleness you have? Monitoring this seems harder than in a leader-based system where you can just track replication lag.
It is harder, much harder. With a leader, you have that single source of truth, that ordered log. You can see how far followers are behind.
Right.
In leaderless, there's no single ordered log. Writes can happen concurrently, maybe get resolved with LWW. So what does lag even mean? It's difficult to measure directly. You often rely more on application level checks or monitoring for specific kinds of anomalies.
No easy replication lag metric then.
Not really. And another point is how inconsistencies get fixed. Many systems use read repair.
Where the read itself notices different versions and triggers a fix.
Yeah, but what if a piece of data with an old inconsistent value is just never read, or read very infrequently?
You could stay inconsistent forever.
Potentially, yes.
Yeah.
Especially if there isn't also a background anti-entropy process proactively comparing replicas and fixing drift. Relying only on read repair for infrequently accessed data can be risky. You need some active scrubbing mechanism too.
That highlights the need for robust repair, not just passive fixing.
Absolutely. And, there is research going on trying to figure out better ways to measure staleness in these leaderless systems. People are trying to model the probability of stale reads based on NWR, network conditions, things like that.
So you can maybe quantify the eventual part of eventual consistency.
That would be the goal. It's not common practice in most off-the-shelf systems yet, but getting a better handle on quantifying that probability would be incredibly valuable.
Okay, so let's try and wrap this up. We've covered the basic idea of quorums needing enough nodes for reads, R, and writes, W, and that key condition, W plus R greater than N, which aims to ensure overlap so reads likely see recent writes.
Right, the probabilistic guarantee.
We talked about the trade-offs relaxing that condition for maybe better latency and availability, but at the cost of more potential staleness.
Yep, the consistency availability trade-off.
And then we dove into the weeds a bit. Sloppy quorums, concurrent writes and reads, partial failures, node recovery, all these ways that even with W plus R greater than N, you can still end up reading old data in practice.
Exactly. It paints a picture where quorums are a powerful tool. Definitely. But in leaderless replication, they're about managing probabilities, not providing absolute guarantees on their own. Understanding those nuances, those edge cases, is just crucial if you're building or running these kinds of systems.
Yeah, this has been super insightful. It really drives home just how complex ensuring consistency is when you don't have a single leader managing everything.
It really is.
And it makes you think, okay, if basic quorums have these limitations, what else do you need? What other strategies come into play when you have really, really strict consistency needs? But maybe that's a topic for another time.
Could be. There's definitely more to explore there with transactions and consensus.
For sure. Well, thanks for walking us through all that today.
My pleasure. Good discussion.
And thanks to all of you for joining us on the deep dive.